Hello calculus students and general seekers of truth. Now in this video we are going to take a look at an example of particle motion, but this time if you notice what we're dealing with here is not a given position function but rather a velocity function. So that's going to make things a little bit different. But let's start out with what we know about the question. So we want to find the average acceleration between 0 and 5 seconds. Now average acceleration is a fairly simple calculation, so we just have to make sure not to mix it up with other types of accelerations. So this is the change in velocity over the change in time. So this is change in velocity over change in time. So for this particular problem, the average acceleration would be between 0 and 5 would be v of 5 minus v of 0 divided by 5 minus 0. V of 5 would be negative 32 times 5 plus 18 minus 0 times negative 32 plus 18. So that's just going to be 18, all of this over 5. So we work that out. We know that the 18s are going to cancel. This is 150. Well, actually what we have left here is negative 32 v, negative 32 times 5 divided by 5. So what we're left with here is just negative 32. And our units here would be meters per second per second. So another way to say that is meters per second squared. Now you may or may not be wondering, why is it that stuff canceled out so easily here in this particular case? 18 and 18 is, it just magically cancels, and then we just have 5 and 5 and that just magically canceled. You know, did I just pick this problem so that it would be super easy for me to do arithmetic, or is there something else going on here? Well, in this case, it happens to be the latter. Sometimes I pick numbers that are really nice, and sometimes I do it by accident, but that's rarely ever the case. In this situation, it's really a matter of seeing that the derivative of velocity is acceleration. So here is the acceleration function would be equal to, let's see, negative 32. So the derivative of the velocity function is nothing more than negative 32. So what that means, that the acceleration at all points in time, at all possible moments, is always negative 32. So the average acceleration will always be negative 32, because acceleration here is a constant, right? So if we pick something like, let's say you were to graph the acceleration function, this is t and this is a of t, then your acceleration function wouldn't be very interesting. It would just be negative 32 the entire time. Okay, so for this case, it happens to be that way, that you have an acceleration that's constant. In other cases, it might not, and this number might change for other intervals. But I just wanted to point that out in addition to just doing the problem. Now moving on to this part, we're asked to find its maximum speed. All right. So the key word here is speed, and remember that speed is the magnitude of velocity. Since we're dealing with just a singular motion or singular direction, just back and forth, speed is essentially the absolute value of velocity. So we're going to look for places where velocity is at a maximum, and we'll look for places where velocity is at a minimum and negative, and see which numbers are bigger. Now our velocity equation is equal to negative 32t plus 18. So if we want to find the maximum of this, well, we take the derivative and we get negative 32, and we can set this equation equal to 0 to try and find what the local maximum really is. But you see that there is no value of t for which the derivative of velocity is equal to 0. So we can say here that v of t has no critical points. So that basically means it has no relative extrema. Because when you think about this, v of t is essentially a straight line that goes this way from, and has the y-intercept at 18, and the slope here is always equal to negative 32. So the maximum speed that occurs here is either going to occur here at 0 or at the other endpoint, which is 5. Excuse me, I did not mean to suggest that this point here is 5. I meant merely to suggest that it's going to be, so somewhere here, right? So 5, I don't know if that's before or after this, but it's either going to happen at, the maximum will either happen at 0 or it will happen at t equals 5. So let's check this. V of 0 is just going to be 18, nothing special there. V of 5 is going to be negative 5 times 32, which is negative 160, plus 18, which gives me negative 142. So I need to update my picture a little bit. I think the the 5 is actually like way over here somewhere. Okay, this is not drawn to scale at all. Well, velocity has a maximum here at v of 0, 18, and it has a minimum on this interval at negative 42. But remember that we're talking about speed. So speed is always positive, and it's the magnitude of velocity, or the absolute value of velocity. So if we take a look at speed, right, we have to take the absolute value of these results. And so what that will give us is effectively, let's see, that all these absolute values here. So this is still 18, and this is equal to 142. So that means the maximum velocity, the maximum speed occurs at a value of 142 meters per second. Now finally, we have a question that's very tricky. What is the position of the particle at t equals 1? Notice that all we're given here is the velocity function. We know that this is equal to 32t plus 18. Now keep in mind that the derivative of the position function is equal to the velocity function. So it's like we know that the derivative of the position is equal to negative 32t plus 18, and we're asked to find what is the position function. Okay, so this is something fairly new that we may not have done up to this point, but what we're going to do is we're going to find, this is called, the antiderivative. Instead of taking the derivative, we're going to figure out, we're given the derivative, and we're asked to figure out what was the original function. So what is the antiderivative? Now, this is a subject that's very deep and rich and quite complicated, but we're going to approach it in a very systematic way, at least for these simple ones. So if you look here, this is a polynomial with a degree of 1, so its antiderivative must have had a degree of 2. So you must have had a t squared here, and you must have had an 18t. Now how do we get, what number do we put in front of here in order for us to get negative 32? Well, that shouldn't be too surprising that it would be negative 16. So we're taking negative 32 divided by this 2, and this gives us negative 16t squared. Now we can actually take this step one more. There's another important part to this, and that's a constant. Okay, so because if you take the derivative of this, s of t, the constant's going to go away, but there could have been some sort of constant here. So we're going to put c, we're going to write c right there, where c is some constant. And in order to really have a complete position function, we need to figure out what c is actually equal to. Well, let's go back here, and we can see from the given that its position, right, at t equals 2 is negative 31. So that means when t equals 2, s of t must have been equal to negative 31. So we know that s of 2 is equal to negative 31. So now we can do some work here. Negative 31 is equal to negative 16 2 squared plus 18 times 2 plus c. So negative 31, excuse me, is equal to negative 64 plus 36 plus c. Negative 31 is equal to negative, this is going to be 28 plus c. So that means negative 3 is equal to c. So now s of t is equal to negative 16t squared plus 18t minus 3. And we wanted to know the position at t equals 1. So we plug in 1 for t. And this will give us negative 16 times 1 squared plus 18 times 1 minus 3. So this is negative 16 plus 18 minus 3, excuse me, minus 3. So that's 2 minus 3, so that's equal to negative 1. Okay. So there you have it, a new sort of concept here called the antiderivative, right? And notice all of the steps here, and in particular this constant c. We'll continue to explore antiderivatives further in this class, but this is a very, very gentle and brief introduction to the concepts. As always, ask for help if you need it. Thank you for watching, and have a wonderful day.